Good afternoon, everyone. So, in today's class, we are going to discuss about quantum mechanics. I had already taken the class through Zoom in online in I think March, but many of you have not attended the classes or could not attend the classes because of the net problems and all. That is why I am recording this video and I will upload it in the Google Classroom so that everyone can see the lectures and to study yourself. So in today's class we are going to discuss about quantum mechanics, but before that we need to know why should we study quantum mechanics, or what was the need of the scientist to use quantum mechanics. So it was in early 20th century or the late 19th century that some phenomena were discovered, but scientists were unable to explain them with the help of classical mechanics or classical electrodynamics. For example, if you take the stability of atom or the atomic model, line spectrum of hydrogen atom, photoelectric effect, Compton effect, pair production, all these effects, they were invented, but they could not explain why or what was the reason behind those phenomena. For example, if you take the stability of atom, so before Bohr model came in, there was Rutherford's model, atomic model, which stated that there is positive charge which is contained inside the nucleus of the atom, and it was in a very small portion, and the electrons, they were orbiting around that positive charge, or they were orbiting around the nucleus, and they can orbit in any orbital. So this was Rutherford's model, but it was faulty, as you already know, you have studied in 10 plus 2, because if the electrons, they rotated in any orbital, then what happens? Whenever rotation happens, acceleration is there, so they face some acceleration, and any accelerated charge particle, they emit radiation, and what will happen? They will lose their energy, and after a certain time, orbiting with smaller and smaller orbits, they eventually go to the nucleus and fall on it. And as a result, the atoms will be unstable. But the case is not so, because atoms are stable. So atomic stability was under question. Then came the line spectrum of hydrogen atom. So when they got the spectrum, if electrons could orbit in any orbital, the spectrum should be band spectrum, or you should get one intensity versus frequency curve like this. But they got lines. That means for particular frequencies, they got some amount of intensities. For the other frequencies, the intensity should be, or intensities were almost tending towards zero. Again, this was unexplainable using the classical concept. Then came Bohr, who stated that the electrons, they revolve around the nucleus, not in any arbitrary orbital. They revolved in some specific orbitals. Those orbitals were known as stationary orbitals, because the electrons, they do not lose energy while orbiting around those specific stationary orbitals. And what was the specification? The angular momentum for each orbital was nh by 2 pi, where h is the Planck's constant and n was any integer. And if those were fixed, then it specifies, or it explains the stability of atom, as well as the line spectrum of hydrogen atom also. Similarly, there were photoelectric effect, you have already studied in 10 plus 2, pair production, Compton effect, spectrum of black body radiation, which was not explainable by classical mechanics. So they used, or quantum mechanics came. The main assumption was of quantum mechanics was the quantization of energy. Actually, some people confuse it with their, that quantum mechanics is for small particles and classical mechanics is for big particles. That is not the case. Quantum mechanics is the more general thing. So it is a generalized form, under some limit, it is transformed to classical mechanics. But quantum mechanics is the generalized form where the quantization of energy is really very important. So no, it is not that all the things happening in the subatomic levels, this means that it will be treated by quantum mechanics. Not the case. But the quantization of energy is very, very important. Now, while we discuss the spectrum of black body radiation, so it is in our syllabus, we will study it in details. So before we discuss this, first we need to know what a black body is and what do you mean by such radiation or black body radiation. Actually, every material or every particle which we see in daily life, they emit some amount of radiation. That is why we are able to see it, frankly speaking. So basically, at room temperature, the most of the radiation is in the infrared region. That is why they are not visible to us. Those particles which have the radiation in visible light region, only they are visible to us. Now, suppose you take a iron rod and you are rising its temperature. So first you will see one gray or black iron rod, then you start increasing the temperature. What will happen after a certain point? It will be red hot. Red hot means it will emit radiation in the red light frequency region. Further you heat it up, so it will start emitting frequencies, emitting radiation of all frequencies. As a result, you will get a white light radiation. So thus we see that all bodies absorb radiation as well as emit radiation, and there is absorptive power. There is a term called absorptive power and emissive power of every radiating body. The emissive power is given by energy emitted per unit area, per unit time, per unit range of wavelength or frequency. Similarly, absorptive power is the ratio of heat absorbed by that particle or absorbed by the body per unit surface area divided by the heat or radiation fallen on the body. Now, a black body is a body which has absorptive power 1. That means it will absorb all the radiation which will be incident on the black body. It will not radiate or it will not reflect back any radiation. But if a black body is heated to different temperatures, then it emits radiation of different frequencies. So a black body can emit or absorb radiation of all frequencies. Now, depending on the temperature, it will emit radiation of some frequencies more and some frequencies less. This we can see in the energy density versus frequency or energy density versus wavelength curves. So how we will discuss about the energy spectrum later. Before that, we need to know about the black body a little bit more. So a body at a constant temperature is in thermal equilibrium with its surroundings and must absorb energy from them at the same rate as it emits energy. So at thermal equilibrium means the number or the rate of emission is equal to the rate of absorption. And the ability of a body to radiate is closely related to its ability to absorb radiation. So a good absorber is always a good emitter. Now, a perfectly black body will have the absorptive power to be 1. That means the whole radiation will be absorbed. But practically, it is not possible because we do not have such material which has 100% efficiency to absorb all the radiation. That is why for practical purposes we construct black bodies. Now, how do we construct black bodies? So here is an example, or I could say a block diagram of a black body. You say that it is a spherical black body with two walls. The inner walls are coated with lamp black, which is 95 to 98% absorbent of radiation. That means it absorbs 95 to 98% of the radiation and reflects the rest. So the inner walls are coated with lamp black, and this is a hollow spherical shape, and there is a small opening here. It is known as the orifice through which the radiation enters. Now, the wall, which is just opposite to the orifice, is not plane. It is rather in conic shape. The shape is given so that a ray which is incident normally through the orifice does not go back through the orifice. That is, it is used to capture the all the radiation. It is used so that any radiation can does not go out from the black from this body. So if it captures all the radiation and does not reflect back any radiation outside, it will be treated as a black body. So the cavity walls, they are constantly emitting and absorbing radiation, and this radiation is known as black body radiation. Now, as I said, I will now discuss about the intensity spectrum for black body radiation. That is, we have plotted along the y-axis the energy density, u nu, d nu, and here the along the x-axis the frequency. We see that the black body has emitted all the wavelength, but the rate is different for different wavelengths. For some wavelengths the energy density is higher, for some it is less. At a particular wavelength lambda m, we get the maximum energy density. And see, look at these two pictures. Here it is at t equal to 1200 Kelvin, and this is for 12 t equal to 1800 Kelvin. We see that the lambda m value shifts towards the right if we plot u nu versus nu, the frequency. Sorry, this is nu m. Nu m shifts towards right if we plot u nu versus nu. Similarly, if you talk in terms of the wavelength lambda, we will see in the next page that lambda m, they shift towards the left. That means the lambda m value decreases if you increase the temperature. As a result, lambda m into T is constant. It is known as the Wien's displacement law. And as you increase the temperature, the graph or the peak of the graph increases. The total energy emitted per second per unit area increases rapidly with increasing temperature. Okay, so the peak here, the peak is smaller than this peak, and the bigger peak is corresponds to a larger temperature, 1800 Kelvin. Now, if we see the energy density versus lambda graph, we see that the lambda m value, this one, the blue dotted line is the lambda m value for the blue curve, which is at 4500 Kelvin, and the red dotted line is the lambda m value of the red curve, which is at 5500 Kelvin. So the lambda m value shifts towards left as you increase the temperature, but for all the graphs lambda m into T will be constant. Now from these graphs there were two observations. The first one was Wien's displacement law, which we already have discussed, that is lambda m into T equals to constant. The next one is the Stephen's law. Stephen's law stated that the total energy emitted per unit area per unit second is proportional to T to the power 4, or E is equal to sigma T to the power 4, which is where sigma is the Stephen's constant, or sometimes called the Stephen-Boltzmann constant. So these were the observed phenomena from the black body radiation spectrum. but there were no equation which could explain the graph. Scientists, they tried to explain the graph with the classical laws, but they were not able to do it completely. They did it part by part. For example, if you take the Wien's distribution law, it is valid for the low wavelength limit. And the Rayleigh-Jeans law, it was valid for the high wavelength limit. So Wien's distribution law or Wien's law is given by u lambda d lambda. U lambda d lambda gives you the energy density is equal to a by lambda to the power 5 b into e to the power lambda kt d lambda, where a and b are constants. And the Rayleigh-Jeans law, it was applicable in the higher wavelength limit, which states that u lambda d lambda is 8 pi kt by lambda to the power 4 into d lambda. So the Wien's law was applicable for this lower wavelength limit, whereas the Rayleigh-Jeans law, it was applicable for the higher wavelength limit, this one. But there were no a single law which could explain the whole graph. Now, to know how to explain the whole graph, we first need to know what Rayleigh-Jeans did or what Wien's did. So this is the derivation of Rayleigh-Jeans law. Now we need to know the assumptions, because the assumptions for Planck's law later, we will see that they were a kind of same with a little bit of modification. So first, the assumptions of Rayleigh-Jeans law, which states that thermal radiation inside the cavity is full of standing waves. As you know, two waves which go in opposite direction, they superpose and give us standing waves. So definitely the cavity should be full of standing waves. Now the next point, each standing wave is equivalent to a classical simple harmonic oscillator. That is the catch. A classical simple harmonic oscillator, it was the assumption of Rayleigh-Jeans. So he assumed them to be a classical simple harmonic oscillator and took the average energy of such oscillator at T temperature to be kT. This is according to the classical equipartition theory of energy. Now we got the average energy of each oscillator to be kT, and if the number density be n nu d nu, then the energy density will be the number density multiplied by the average energy. Simple. So number density of such oscillator is n nu d nu equals to 8 pi nu square by c cube into d nu. Now the derivation of n nu d nu here is not necessary, but you can find it in the statistical mechanics notes or statistical mechanics classes. In while we had studied statmech, we got the density of states GPdP. So you got a formula for GPdP, multiply it by 2 to get the NPdP, that is number of particles or density of numbers, actually NPdP per unit volume divided by V, and you will get a formula. Now if you use the P equal to H by lambda there, you will get this equation. So its derivation is not necessary for now. Just remember the formula. N nu d nu is 8 pi nu square by c cube d nu, and multiply it by kt. So you get u nu d nu. We get 8 pi nu square kt by c cube into d nu, and you convert it by u lambda d lambda. Sorry, this will be d lambda because nu equals to c by lambda. So you replace nu equals to c by lambda. So d nu will be c by lambda square into d lambda. Mod of d nu will be c by lambda square into d lambda. Put it in this equation. Put it in this equation. You will get the last equation, which gives us the Rayleigh-Jeans law. Now, as I said, this law is valid in the higher wavelength region. the discrepancy between the theoretical conclusion which state that u lambda should be infinity at t equal to 0, this is the theoretical line, red one, and the experimental evidence, that is u lambda should be 0 at t equal to 0. The discrepancy between the theoretical conclusion and experimental evidence for Rayleigh-Jean's law at the lower wavelength region. This phenomena is known as ultraviolet catastrophe. Okay, now we come to Planck's theory. Planck gave us the formula which was able to explain the whole in energy density versus frequency pattern. So for that, he also did some assumptions, and those assumptions were all bodies inside the black body will act as black body. They will also emit and absorb radiation, and the absorbency will be 100%. The atoms in the walls of the black body will act as a quantum harmonic oscillators. So this is the main difference between Planck's theory and Rayleigh-Jean's theory. They assumed them to be harmonic oscillator, but they assumed them to be classical harmonic oscillator. But Planck assumed them to be quantum harmonic oscillators oscillating with a specific frequency nu. So this is the main thing. So classical harmonic oscillators, they can have any amount of energy, but as I said, the main thing of quantum mechanics is that energy is quantized. So quantum harmonic oscillators of frequency nu can have only energy n h nu, where n is any integer. And these oscillators can go from one energy state to another energy state by emitting or absorbing energies only which will be multiple of h nu, obviously. So this is the main thing. Now, Planck's radiation law states that En equal to nh nu, where n can be 0, 1, 2, 3, everything. The average energy of an oscillator is given by E bar equals to E by N, where this E is equal to summation over En into Nn divided by N. We will do this in details. So first we have to find out this average energy of each oscillator, and then we will multiply the average energy by the number density. Thus we will get the energy density. Now how can we get the average energy of each oscillator? For that, let capital N be the total number of Planck's oscillator inside the black body, and capital E be the total energy. So energy per oscillator will obviously be epsilon bar equals to capital E by capital N. Let n suffix m be the number of oscillators with energy m into epsilon, where epsilon is h nu. So nm be the number of oscillators with energy m h nu. Then, so there are nm number of oscillators with energy m h nu, n0 number of oscillator with energy 0 into h nu, n1 number of oscillators with energy h nu, n2 number of oscillators with energy 2 h nu, n3 number of oscillators with energy 3 h nu, and so on. So the total number of oscillators will be then n equals to capital N equals to summation over m equal to 0 to infinity nm, and the total energy will be summation m equal to 0 to infinity m into nm into E, or m into nm into h nu. Now we will first talk about the first series, n equal to n0 plus n1 plus n2 and so on. Okay. According to Boltzmann distribution, nr, that is number of particles having energy r into h nu, is given by n0 into e to the power minus r into h nu by kt, or nr equal to n0 e to the power minus r epsilon by kt. Now we put it in this formula. So n0 will be n0, n1 will be n0 into e to the power minus epsilon by kt, n2 will be n0 e to the power minus 2 epsilon by kt, and so on. Now you can take n0 common, and we have assumed x equal to e to the power minus epsilon by kt. So the expression or the series reduces to n0 into 1 plus x square plus and so on. It is a series of 1 by 1 minus x. So it will be n0 by 1 minus x. Put the value of x, you get n0 by 1 minus e to the power minus epsilon by kt. Similarly, we will find out the series of E. So E is given by summation m epsilon nm. So the first one will be m will be 0, epsilon will be epsilon or h nu, nm will be n0 e to the power 0. So eventually it will be 0 into something is 0. The second term, which is for m equal to 1. So m will be 1, epsilon will be epsilon, and nm will be n1, which is given by n0 e to the power minus 1 epsilon by kt. The second term, m will be 2. So it will be 2 epsilon n0 e to the power minus 2 epsilon by kt, and so on. Now if you take out epsilon n0 e to the power minus epsilon by kt out, you will get 1 plus 2x plus 3x square plus dot dot and so on, where x is e to the power minus epsilon by kt. Again, this is an infinite series. You can express it by 1 minus x whole square. So you get the formula of E like this. So what will be epsilon bar? The average energy is the total energy E by total number of oscillators N. And if you put those values in this expression, you will get epsilon bar equals to epsilon into e to the power minus epsilon by kt divided by 1 minus e to the power minus epsilon by kt. Now if you divide both the numerator and the denominator by e to the power minus epsilon by kt, you will get epsilon by e to the power epsilon by kt minus 1. Put the value of epsilon to be h nu, you get epsilon bar equals to h nu by e to the power h nu by kt minus 1. So we got the average energy epsilon bar. Now multiply it with the number density and you will get the energy density. So U nu d nu is the number density multiplied by the average energy, and it is equal to 8 pi h nu cube by c cube d nu by e to the power h nu by kt minus 1. So this is the Planck's radiation formula in terms of frequency. Now if we want to get the Planck's radiation formula in terms of wavelength, just replace nu equals to c by lambda and mod d nu equals to c by lambda square into d lambda. Put it in the formula and you will get u lambda d lambda equals to 8 pi h c by lambda to the power 5 d lambda by e to the power h c by lambda kt minus 1. So this is the Planck's radiation formula in terms of wavelength. So you can derive it on your own from this expression. You do it yourself. I know that you will be able to do it. Now in the next class, we are going to see how the four laws, Wien's displacement law, Stephen's law, Wien's radiation law, and Rayleigh-Jeans law. These four laws can be derived from this one equation, the Planck's radiation formula of black body radiation. Now, if you have any doubt in understanding the class or understanding any derivation, you must write it in the comment section of the classroom, and we will discuss about it later. So for then, study yourself and study hard, because The exams may happen online, as the I don't know officially till now, but we are hearing some news about that. So prepare yourself for the exams. Okay, goodbye.